I think becoming comfortable with conditional probability is one of the more important things that we all need to do just in our every day-to-day living. And it's also one of the most important things that we need to do if we're going to be an effective business analytics practitioner. So in this unit, we want to talk about, well, what does conditional probability allow us to do, and why is it just so important in our day-to-day life and in business analytics? And for me, I like to think of business analytics as pretty much taking the viewpoint that information matters. What we do in a particular situation, what products we try to sell an individual, what plans we hope an individual signs up for, how many parts we need to reorder. All of that hinges upon the most complete understanding or knowledge about the world that we have. We're not going to try to sell pet insurance to somebody that doesn't even own any sort of pets. So with the theme of business analytics really being information matters, we'd like to talk about, well, how does a more complete knowledge of the current state of events change the probability of events we might be interested in? If we're studying what kind of items shoppers have in their shopping cart when they check out, how does knowing that a cart has pasta sauce, spaghetti, and wine change the probability that they also have garlic and tomatoes? We would like to know, based on our most current understanding of reality, what's the best estimate of probabilities of events of interest. Now, one thing that I've done often at the University of Tennessee is work with the development office. And the job of the development office is to engage alumni of UT and try to get them to give back to the university, make some sort of donation, and however small is great. And one big problem that the alumni office would like to solve is figuring out what sort of characteristics are associated with someone eventually becoming a major donor, someone who donates over $25,000 back to the University of Tennessee. Now, in general, what happens if you work for the development office, you might be assigned to make a lot of telephone calls, call up alumni, and see if they're in a place in their life where they're ready to give back to the University of Tennessee. And one bit of data that we might have about recent alumni is that overall, 15% of recent alumni, say who graduated in the last 5 years, might donate something back in the following 5 years. So that might be a general figure that is true from past data that's been collected, but that probability might change depending on what type of alumnus that we're talking to. What if we know that the alumnus that's on the phone is a woman who graduated without any sort of student loans, she was a member of a sorority, and she was also a business analytics major? Well, with more information about this alumnus, maybe her probability of donating is higher than that overall probability of 15%. And if you go work for a credit card company or any sort of company that regularly experiences some sort of fraud, well, developing fraud detection algorithms and making intelligent decisions about which transactions are legitimate, which ones are fraudulent, is a pretty important thing to do. So fraudulent credit card transactions, big headache for credit cards like Chase, and fraudulent transactions are relatively rare. We might know from past data that maybe 1 out of every 100,000 charges are fraudulent, but what if we have additional information about one particular purchase? What if we know that the owner of this particular credit card usually uses their card to purchase gas and groceries, they live in Florida, and kind of out of the blue, this credit card was just used to purchase a big screen TV in Alabama? That seems like an unusual purchase for that credit card, and so how does that change the probability of that transaction being fraudulent? Without knowing any information about it, it might stick at 1 in 100,000. But given that it's an unusual location in an unusual kind of characteristic of item here, then maybe that probability is quite a lot higher. Likewise, Amazon, Target, Walmart, Best Buy, any sort of online retailer is very interested in getting you to buy more. And so they like to study combinations of items that tend to get purchased together. So they might know that the probability that a random customer buys a wireless mouse might be really small. Maybe only 0.15% of transactions involve wireless mice at checkout. However, maybe from their data, they might know that that probability changes depending on what else is in the cart. They might know that, all right, if someone has a laptop already in their cart and they have some additional RAM as well, the probability of them also wanting to purchase a mouse might skyrocket up from 0.15% up to 12%. So the more information that we know about reality, the better that we're going to have an idea for what the probability of various events of interest are. And so the study of conditional probability is trying to kind of talk about how we go about and do this. So we might start out with some overall fraction of time where some event occurs in general, the probability a transaction's fraudulent, the probability an alumnus donates to UT in the next 5 years, or the probability someone has a wireless mouse in their shopping carts. And we would like to update that probability based on additional information that we know about the world. So a weird location for the transaction. These other particular items in the cart, we would like to figure out, what fraction of the time does our event of interest occur in a much more specific scenario, given additional information that we know about reality. And so to flesh out how conditional probability works, how we do this updating of probabilities to reflect our current understanding of reality, we want to introduce a bit of terminology to make the discussion flow a bit more smoothly. So when we talk about conditional probability, there's two probabilities that we're going to focus in on. The prior probability is that overall fraction of time where some event of interest occurs. That's just the overall probability of some event happening. That 1 out of every 100,000 transactions being fraudulent, 15% of UT alumni donate back to UT in the following 5 years after graduation. That's just the overall long-run fraction of time something that we're interested in occurs. And what we'd like to do is we'd like to update that probability based on additional information that we know. We would like to come up with the posterior probability of that event. We'd like to know, what fraction of time does that event occur in a much more specific scenario? Sure, we know that overall 15% of UT alumni give back in the first 5 years after graduation, but maybe among women business analytics majors with no student loans, that probability might be relatively high, maybe 50%, 80%. We'd like to update that probability here. Now, if you're in business analytics, very often you might end up in a case where you have such a large data set that these probabilities can be estimated directly from data. So for instance, if we wanted to know, here's this credit card that was just used in Alabama for a big screen TV purchase. Normally this is used in Florida for gas and groceries. We can go and look at, say, entire transactional databases of all customers that are out there, see, just how often does a customer tend to shop in a different state for a different type of item that they usually purchase. So we might be able to say, okay, we were able to identify, say, 5 million times this sort of purchase happened, a different state, a different type of item. And out of those 5 million times, 100,000 were fraudulent. So we'd be able to update from that 1 in 100,000 to the 100,000 out of 5 million, kind of a boost in that probability. So that's what we would like to do. We want to go from the prior probability of an event happening, just the overall long-run fraction of time where that event occurs, to the posterior probability of that event, the long-run fraction of time where that event occurs, but in a much more specific scenario that incorporates the information that we have about reality. Now, we're going to have to be really careful, actually, when doing this updating because for whatever reason, the human brain seems to be hardwired to get these calculations wrong. we don't intuitively quite get how to go from prior to posterior probabilities. So we're really going to have to rely on the mathematics and the laws of probability here to get us to the correct answers. And just to illustrate, how bad we really are at conditional probabilities, here's a classic problem that all classes in probability introduce. So let's imagine that you go into the doctor and you end up getting tested for a relatively rare disease, kind of on a whim. So the test unfortunately comes back positive for this rare disease. And so we'd like to know, well, what's the probability the person actually has that disease? And let's say the tests are pretty good here. So first off, this disease really is quite rare. Maybe the probability someone has it is a scant 0.04%. But the tests are really well developed. They're really quite good here. If the individual has the disease, there's a 99.9% chance the test will come back positive. So if you have it, almost with certainty that test is going to come back positive. And also vice versa. If the individual doesn't have the disease, let's say there's a 98% chance the test comes back negative. So little chance of a false positive. If it comes back negative, you probably don't have that disease. It's not going to miss it all that frequently. So here's our information. We got tested for this rare disease. Not that many people have it. The tests are pretty good. Our test came back positive. So what is the posterior probability of us having this disease given the positive test result? And so here are a bunch of options. I want you to look through those and just think which one seems the most reasonable to you. And I'll give you a few seconds. All right, so we'll work out the answer to this mathematically, but spoiler alert, the answer is going to shock you. Now, there's another kind of fun, classic problem that I like talking about, a little bit sexist, so you'll have to kind of forgive that, but it's meant to play a little bit on stereotypes, so you'll have to forgive it in this case. So here's the scenario. So you're hanging out with one of your friends, and your friend shows you a picture of a woman on his phone. So you think she's cute, so she asks, hey, what does she do for a living? So your friend replies, well, I don't really remember, but I know she's one of two things. She's either a waitress or a librarian. Not really sure which one it is, but one of those two. So question number one, what is the probability that she's a waitress versus the probability she's a librarian? Which of the two is more likely? All right, well, the conversation continues, and you ask for a few more details about her. You want to get to the bottom of this. And so your friend tells you that, okay, well, she's typically pretty quiet. She likes to read. She's very intelligent. She dresses somewhat conservatively. And, oh yeah, she wears glasses. So a little bit of additional information about this woman. And so we'd like to incorporate that information to a better estimate of the probability she's a waitress or a librarian. So given this additional information, kind of down to a T, a good description of what a librarian kind of seems like, at least a stereotype of it. Given this additional information, now what's more likely? Is she a waitress or a librarian? So keep those answers, the positive test result and the answer to the waitress versus librarian problem, in the back of your head, because we'll solve these mathematically, and it'll illustrate that we just really aren't that great at doing this updating from the prior probability to a posterior probability. Now, before we get into the mathematical formalism here, I want to go over one more example in a bit more depth, without any math, just to kind of hit home the fact that we're just not good at doing these probability calculations, that we're just notoriously bad at guessing conditional probabilities that reflect, the best amount of information that we have about the world here. And this is the classic Monty Hall problem. If you've ever seen the movie 21, they talk about it there. This is pretty much all over the place. And it still continues to be controversial to this day because the answer is really that surprising. So let me head on over actually to the website, which provides a nice little interactive game for this. And here's the deal. So we're a contestant on a game show hosted by Monty Hall, and the game that Monty is going to have us play is the three doors game. We'll call it that, why not? So here's the deal. We're presented with three doors, door number 1, door number 2, and door number 3. And Monty says that behind one of these doors, there is a brand new car. And behind the other two doors, there's a goat. So obviously we would prefer to have the brand new car. And so that's going to be our goal. We're going to try to pick the door with the brand new car. So Monty Hall says, well, go ahead and get started. Pick your favorite door. So I'm going to pick door number 1 here. And here's the twist. Monty says, well, that's a really great choice you have, but what about this? And he goes and opens one of the two remaining doors. And in this case, what he's done is he's opened and revealed a goat behind door number 3. And in fact, since he's always able to reveal a goat behind one of those two doors, he's always going to reveal a goat and ask you again, all right, well, would you like to stay with the door that you originally picked, or would you like to switch? In this case, would you like to switch to door number 2? So the question is, what is the optimal strategy here? Should we stick with our guns and stay with the door that we originally picked? So we switch, in this case, to door number 2, or does it not even really matter here? Monty is placing the car kind of randomly behind doors 1, 2, and 3. They're all equally likely here. So there's no reason to suspect that, going into it at least, that any one door is any more likely to have the car behind it than the other. So let's just play around just a little bit. So I'm going to say, I really like the door that I originally picked. I'll stick with door number 1. So this will be our final answer, so to speak. We click on it and ta-da, I just want a brand new car. Fantastic. Still have to pay the taxes on it if you win a car in a game show, and taxes can be really quite expensive. But we won with that decision. The question becomes, is that the right thing to do all the time? Should I always stick with the door that I originally picked? Let's go ahead and now pick door number 3 as our favorite door and play the game again. So the car is randomly placed behind doors 1, 2, or 3. Goats are behind the remaining 2 doors. So we pick door 3 and Monty says, excellent choice. Now I'm going to open what's behind door number 2 to reveal a goat, and he's going to offer us the chance to switch again. Do we want to stay with door number 3, or would we like to switch to door number 1? And since I stayed last time, I'm going to go ahead and switch. Maybe door number 1 is lucky for me today. I'm going to click door number 1, and I get stuck with the goat. Should have stuck with my guns in this case. The car was behind the door that I originally picked. Let's play one more time. I'm going to pick door number 2 to start out with. Monty says, fantastic choice. I'm going to reveal behind one of the remaining 2 doors a goat, and he shows us a goat behind door number 3. And he asks us once again, do we want to stay with the door we originally picked, door number 2, or would we like to switch to door number 1? I'm going to select door number 2, and I won the brand new car again. So in this case, 3 out of 3 times, the car actually was behind the door I originally picked. Maybe I'm just having a really good streak of good luck. What's the right thing we should do in general? Should we stick with the door that we originally picked? Should we switch? Does it really not matter whatsoever? That's what we'd like to get to the bottom of. So a little bit of a background behind this problem and why it is so controversial. So you may have heard of a woman named Marilyn Vos Savant. She had a column in Parade magazine way back before any of you guys were born, where she actually talked about the solution to this problem. And she's well recognized as someone who's had, one of the highest IQs in the entire world. She's extremely smart, extremely insightful. She gets all of this stuff that we all wish we could get here. So she actually posed this problem to the readers and wrote a solution. And in her column, Ask Marilyn, she said that the optimal solution was that the player should always switch. So in those 3 games that we just played, switching would have lost every single time. But she says that the optimal strategy is always to choose the door that Monty didn't reveal the goat to be behind. Abandon the door we originally picked, take the other one. And that caused a lot of uproar In fact, she got tons and tons and tons of letters from readers vehemently disagreeing with her. And not just from, everyday folk, but from very educated individuals with PhDs in various fields, PhDs in math, people that really were quite good at math and logic here, who just did not feel like she got the answer right. So it ended up that she ended up writing a bunch more columns, kind of elucidating why the optimal strategy should be to always switch. And the crazy thing is that even after further elaboration, only a little over half of the general public really believed her solution, and not every academic believed her either. Only about 71% of academics really bought into her solution that always switching is the optimal and correct strategy. So let's kind of go over what is the correct strategy, why is always switching the correct strategy, and why do we get it wrong? All right, so what do people tend to think the right thing to do? Well, my intuition, definitely the first time I heard about this problem, and probably your intuition as well, it suggests that once the goat's revealed behind one of the doors, well, there's an equal chance of the car being behind either of the remaining two. After all, the car was randomly placed behind door 1, 2, and 3, so when Monty reveals a goat behind one of the other doors, that doesn't change that fact at all. If it was equally likely to be behind one of those 3 doors to begin with, well, it's still going to be equally likely to be behind any of those 2 remaining doors. So it doesn't really matter if you stay with the door you originally picked or if you switch. Most people psychologically would hate to give up a car, so we tend to stick with the door that we originally picked. But it turns out that that's completely wrong. That's not the right line of reasoning. Our gut suggests that there's a 50-50 chance that it's behind the door we picked versus the remaining door that hasn't been opened. But that's wrong, actually. So why is that wrong? Our tuition, almost everyone's tuition immediately says it doesn't matter. Do whatever you want to do. Why is it that the chances are not 50-50 that the car is behind the door you originally picked and the remaining door that Monty didn't open? And this harkens back to one of our discussion points way back in Unit 1, where we talked about equally likely outcomes and when we could assume that all outcomes were equally likely. And one of the talking points that we had was that just because there were 2 options doesn't mean necessarily the chances are 50-50 between those 2. There's 2 options for the outcome of your grade in this class. Either you're going to pass or you're going to fail, but that doesn't mean there's a 50-50 chance of either of the 2 occurring, because it depends on a lot of other things, how much work you're putting into it, your attendance, etc. We know that when there are 2 options, they're equally likely. That only occurs when those outcomes are being picked at random, as if we had put those outcomes into a bag, kind of smushed them all around, and just picked one out at random here. So, initially, yes, the car's location is chosen at random. So, initially, yes, because there were 3 options, the probability of it being behind any individual door starts out to be 1 out of 3. The probability it's behind the door that you picked is indeed 1 out of 3. And so, here's one line of reasoning. Monty is always going to be able to open one of those 2 remaining doors. here's my favorite argument or line of reasoning for why we should always switch here. So, if we originally picked the door with the car and we switch, we lose. Now, that is not up for debate here. If we switch away from the door with the car, obviously we're going to lose here. However, let's imagine that we originally picked the car or the door with a goat. So when Monty goes and reveals a goat behind one of those other two doors, well, if we switch in that case, we're going to win. No matter what, because there always is going to be a car behind that one door that Monty didn't reveal. So here's another way of getting those probabilities. We know that if we picked the door with the car and switch, we lose. If we picked a door with a goat and switch, we win. Well, that means that there's a 2/3 chance that if we switch that we win, because there was a 2/3 chance that we picked a door with a goat behind it. There's only a 1 in 3 chance that we picked the door with the car, a 2/3 chance that we picked a door with the goat. If we switch when we pick the goat, we win. If we switch when we pick the car, we lose. That means there's going to be that 2/3 chance that when we switch, we end up winning. So even after thinking about this quite a lot, people still really had a hard time believing it. That's why, a little over half of the general public were like, nope, it really still doesn't matter. It's 50-50 either way. Even academics still fell for this. It might take a while to really become comfortable thinking about and accepting the answer to this problem here. And in fact, that's one thing that I like about the website is that it is keeping track of the last 200 or so, I think, players of this game. What we see is that, okay, of all the people that switched, right about 2/3 of the switchers ended up winning. Of all the people that didn't switch, about 1/3 of the people ended up winning here. So 2/3 chance of winning if you switch, 1/3 chance of winning if you don't switch here. All right, so there have been generalizations of the Monty Hall problem to multiple doors besides just 3. So 4, 5, 6, etc. doors. And I've put up on Canvas a file called montyhall.r that allows you to play this with a 4-door problem. So what I've done is I've read in the code here. This makes 2 functions, let's make a deal, and then also let's make a deal simulation. And the way that you run them is to just type out the name of the function with no argument. So just parentheses with nothing in the middle here. So this will bring up a diagram and says, all right, here's 4 doors. Pick a door. Let's pick door 4. That sounds fun. 4, door, they rhyme. What could be more fun than that? So here is what Monty Hall does. He says, fantastic choice for picking door number 4. What I'm going to do is I'm going to reveal what's behind 2 of the remaining 3 doors. So he ends up revealing a goat behind door 1, a goat behind door 2, and he offers you the chance to switch to door 3 or to remain with the door you originally picked, door 4. So do you stick with door 4 or do you switch to 3? Enter your door number. And in those 3 examples that I did on the website, I always won by just sticking with the door I originally picked. So dang it, that's what I'm going to do again. I know Marilyn Savant is staring at me with a frown, and I lose here. Let's do it again. I'm going to pick door number 2 here. We get to choose between door 2 and 3. I'm going to switch. There we go, I won. So my question to you is, okay, now that we have 4 doors, what do you think the probability is of winning the car if you stick with the door that you originally picked versus switching to the one remaining door that hasn't had a goat be revealed behind it? And if your answer is that there's a 1 in 4 shot of winning the car if you stay, a 3 in 4 shot of winning the car if you switch, big thumbs up to you, then you've got it. So there's also the second function, let's make a deal simulation. This one you also run with just empty pair of parentheses. This goes and does the whole thing for you. So what it does is it automatically picks door number 1, and then what it does is it automatically stays with that original door. So you can kind of run this a whole bunch of times, And you can see in this case, yeah, we're lose, 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 win, win, lose, lose. So most of the time we're actually losing here. You could write a for loop actually and just go through, say, 1,000 different games and keep track of, well, how many times do we win? How many times do we lose? So if we end up staying with the door that we originally picked, and that's what the strategy is doing in this particular function here, we win about 25% of the time. If we switch, then we would win that 75% of the time. So if we stay with the original door that we picked, win about 25%, lose 75%. Clearly, we want to be switching. So that's the Monty Hall problem, and it's one of the most difficult problems to accept and build your intuition around. And it just really hits home the fact that we're just not that great at conditional probability calculations. None of us would really argue that the prior probability of the car being behind the door that we've originally picked is 1 out of 3 because the car was placed at random. 3 options, each one has a 1 in 3 shot. It's just very difficult to accept that the posterior probability of that car being behind the door we originally picked is still 1 out of 3. We feel like with 2 remaining options, Monty can always reveal a goat behind one of those 2 doors. Each of those 2 options should be originally likely, because that's how the problem started out. And there was just that little tiny twist in logic in that, yeah, that probability of the car being behind the door that we originally picked, it started out as 1 out of 3. It stays at 1 out of 3. The implications, though, is that the probability of it being behind that other door now is 2 out of 3 because 1's been eliminated. So upshot is, whenever we run into calculations that require us to work with conditional probability, we want to take a step back, take a deep breath, realize that, okay, our intuition probably is not going to get us there unless we're Marilyn Boss Savant, and we need to just go through the math, or we need to write out some tables or some other strategy to come up with the right answers. All right, so before diving into the math, what I wanted to illustrate was a more intuitive approach for calculating these conditional probabilities. It's really easy to just get lost in the relatively complex formulas that we're going to introduce to help us out with calculating these conditional probabilities. And I think, seeing how these conditional probability calculations are working, seeing where these answers emerge from is actually kind of infinitely more useful and ultimately satisfactory as well, and it helps build our kind of comfort level with these sorts of problems. So what I would like to do is I'd like to go back to the classic test where we went and got tested for a really rare disease. The test came back positive, and I asked you, okay, well, if this test is pretty good, given that we have a positive test, what's the probability that we have the disease? The prior probability of having that disease was tiny, like 0.04%. The test was really good. If we have it, it comes back positive 99.9% of the time. If we don't have it, it comes back negative 98% of the time. So the test came back positive. Given that vertical bar right here, given the test came back positive, what's the probability that we're infected? So let's reason through this. And the way that I like reasoning through this is to kind of tie this into a real world situation. Let's actually imagine a whole bunch of people going in and getting tested for this disease and see what ends up happening. So here's going to be my strategy. I'm going to create a 100 by 100 grid of dots for a total of 10,000 real people. We're going to administer this test to all of those individuals, kind of work out this probability of what happens. All right, so what we have is this 100 by 100 grid. You probably can't see each individual dot right here, but there are 10,000 total individual dots. Let me see if I can zoom in a little bit there. Ooh, yeah, that's great. So what we know is that the disease is pretty rare. Only 0.04% of individuals have this disease. And so 0.04% of 10,000 works out to be 4. So of these 10,000 real people, let's go ahead and color code the 4 people that actually do have this rare disease with these red dots here. So zooming back out, we find that, okay, there are a tiny little fraction of all of the dots out there. 0.04% of the dots have been color-coded red. So that's kind of the meaning of rare. 0.04% doesn't really look all that impressive here. So what we're going to imagine is that every single individual here, every individual dot, gets tested for the disease. So what's going to happen if they get tested for the disease? What are the results going to look like? Well, we know this test is really good, so that when a person is positive, the test comes back positive with a 99.9% chance. So we'll assume that those 4 red dots in the previous slide here, the test for those 4 individuals come back positive. The test is pretty much always going to get it. Now let's think about the black dots, the individuals that didn't have this disease. Well, the test is pretty good, but one thing we know is that the probability that the test comes back negative when they have the disease is 98%, implying that the false positive rate is 2%. So 2% of these black dots, these people that don't have the disease, are going to come back with positive results. So of the 10,000 people, well, really 9,996 people without the disease, 2% of them are going to come back with positive tests. Now, mathing that out, we get 199.92. Let's just call that 200. So we'll have 200 false positives here. Let's color code these individuals blue. So here are our 10,000 individuals. All the black dots represent the individuals who don't have the disease and their test came back negative. We have the 4 red dots representing the people that actually do have the disease and their test came back negative. And then we have these blue dots, the people that don't have the disease but their test came back positive anyway. 2% chance of that happening, we get a few false positives. So here is how we need to calculate this conditional probability. Given that the test came back positive, what's the probability of having the disease? Well, given that the test came back positive means that we're one of these color-coded dots. We're either red or blue, but we're one of these color-coded dots here. The probability that we actually do have the disease would be the probability that if we were to reach down into one of these dots, we end up picking out one of these red dots out of the collection of red and blue. So what we find is that the answer is really going to be surprising here for what this conditional probability is. We're going to be one of those 204 colored dots. And what are the chances that one of those randomly picked 204 colored dots actually have the disease? Well, there is 4 out of those 204, which works out to be just about 2% here. So here's that crazy thing. Let's go back to that original slide where I gave you those different options here. 2% is actually the correct answer here. So even though this disease is really, really rare, the tests for this disease really quite good here. Even when that test comes back positive, chances are you probably don't have that disease. Even when that test comes back positive, there's really a 2% chance of you having that disease, as we kind of reasoned it through by considering, well, what would happen if we were to apply the test to 10,000 different individuals. So 2 things. Number 1, we're not very good at doing that conditional probability calculation just in our head. Most likely you chose an answer that was really far off. But number 2 is that the probability of having the disease really did change substantially with the evidence that the test came back positive. Remember that prior probability of having the disease was only 0.04%. It shot up by a factor of 50. So we're 50 times more likely to have the disease given that the test came back positive than we were, before we went to the doctor's office to get that test. It just so happens that being 50 times more likely still really isn't all that likely at all. Sure, we found that 50-fold increase in the probability, but it still doesn't turn out to be very likely. And in fact, this has some pretty substantial real-world implications, specifically for tests for COVID-19 antibodies. So I know that when the antibody tests were coming out, I was really hoping that I would be able to get one because I would have loved to have known, hey, did I ever come down with it? I actually visited Boston right before the shutdown for a big conference, And so I was in contact with tons and tons of people who were traveling from across the US, across the world. There's a reasonable chance that I could have run into somebody who had been maybe asymptomatic. So I wouldn't have been surprised if at some points I might have had a asymptomatic case. And so I really wanted to get an antibody test. But here's the kind of the analysis, the analytics, though, with those antibody tests that kind of illustrate that they're sort of not that informative at this point. So as of July 30th, when I went through and looked up the statistics, I looked to see, okay, of all the people in Tennessee, how many tests have come back positive, how many people live in Tennessee, et cetera, et cetera. Because I wanted to illustrate that a positive test for a COVID-19 antibody really didn't actually mean that much. So back on July 30th in Tennessee, there were about 100,000 confirmed positive results of COVID-19. So the population of Tennessee, pretty big, about 6.8 million. And so we're actually in a very similar situation as we just worked through with our example. The prior probability of you having COVID-19, with some remarkably simplifying assumptions that it's kind of distributed just at random through across the state. That's not true, but going with that simplifying assumption, the prior probability would work out to be only about 1.5%. So as of July 30th, it was still a relatively rare disease. And the thing about the COVID-19 antibody tests is they weren't really all that fantastic. They didn't have the track record of this fantastic test in the example here. So here's why the COVID antibody tests really weren't all that important to be going and taking, and you couldn't really take much away from it anyway, is because the prevalence of COVID-19 was relatively rare, the tests pretty good but not fantastic. If the test came back positive, the chances of you having COVID-19 was actually relatively low. Now I'll have you work through that on a homework problem so you can see that, but it ties in nicely to one of those classic examples in the study of conditional probability. Conditional probability answers are very often surprising to us. I do want to hit home that our intuition just isn't set up to do this naturally. We're really going to have to rely on working through examples or working through the mathematics. But I do want to give you a bit of encouragement here. If you just realize that a conditional probability is still just the probability we know and love, the fraction of the sample space where our event of interest occurs, just with a different sample space that reflects the information that we've collected, it's not this kind of mysterious otherworldly being that is going to set us into confusion forever. A conditional probability is still just your standard probability, just with a different sample space than what we originally started with. And why we get tripped up in trying to intuitively come up with these conditional probabilities is that our mind actually just isn't good at identifying what that reduced sample space is, what the change sample space is. So what do I mean by that? Well, going back to the classic result, we started out with that sample space of 10,000 individuals. We're going to assume our identity is kind of randomly picked to be one of these 10,000 dots. And it was pretty easy for us to get what a 0.04% chance of having the disease was. There's 4 red dots. The remainder of the dots were black. Pretty rare that we're going to have that disease. Now, if I threw in that additional information to you that the test result came back positive, well, ultimately our probability calculation still worked out to just taking a fraction, the fraction of red dots out of all the individuals that tested positive for the disease. Where our mind tripped us up is that we weren't able to immediately visualize and digest what that new sample space looked like, with that new sample space being basically these blue dots and red dots combined. It's still 4 red dots divided by 204 total dots for the positive test cases. The probability calculation still proceeds just like that. It's just with a different sample space than what we originally started out with. And so those are the examples that I want to go through where we can actually see how the sample space changes when we add in more and more information to our problem. And so here's where I want to work through a few of these to see just how it goes. And I want to give credit to actually one of our previous UT undergraduates currently in the MSBA program. Scott Lawson, actually, we were working through some conditional probability exercises, and he had drawn some sort of table to come up with an answer for a conditional probability question. And so I was wandering around, and I saw what he was drawing. And I was like, oh, that's interesting. I wonder what that is. So I went over, asked him to explain what he was doing. And the moment that he started explaining how he was working through the problem, I was like, well, that's brilliant. Why haven't I been teaching this all along? And so I really feel like these examples will illustrate how this conditional probability computation works.